I want to see if there's life out there in my lifetime. All these options seem to be 50 years hence, and just very frustrating. I'm an electronic engineer interested in sensors, so I see a potential there.
So I'm probably going to be being broken down by camera autotrophic bacteria by that time. I mean, one of the things I've heard today that I thought was interesting was Charles's comment about, has anyone actually done the calculations of how much potential chemical energy might be lying around in some of these systems for life to actually essentially survive. So that's something that might be well worth a bit of thinking about in terms of a paper. Don't know whether anyone else has got any thoughts at all. Andy?
Just coming from the outside, one of the things that struck me today, and it struck me at previous astrobiology meetings, is the balance between two quite fundamentally different strategies, each of which is extremely expensive, which means you probably can't do both. And one is to invest a huge amount of money in looking at great detail at one specific spot versus spending a great deal of money taking a much more synoptic view and going around and looking for different classes of signals, but doing it over a wide spatial area. Like Alex and Doug, I've worked extensively in the sea, and the trade-off always there is, do you look at one spot in detail and get a very detailed understanding of that one spot but no generality, or do you look generally, in which case you get a nice smooth, smeared low-resolution picture, but you don't have the details at any one spot. Now that's fine, because we generated now, as Doug has shown us, technologies that merge those two together, which are AUVs and gliders. So you start to link those two together. But when you've got one shot at it, and it costs you hundreds of millions of dollars, have you weighed up the balance between, as an extreme example, if you had one city on the face of the Earth only, and then you went and landed a probe, but it just happened to be on the other side of the planet, you'd miss it.
Difficult.
There's a lot of talking going into probes and going in, but if what you're looking for is distributed very stochastically and very randomly and not at high density, so you stand a very high chance of missing it. Whereas if you are circulating the probe and using other techniques for looking, maybe you at lower resolution, so then you have a sensitivity problem. But maybe you are more likely to pick something. I don't know. This is a question coming from out and completely outside the field. I guess people in the field must have resolved that issue, because both processes are clearly going ahead. But it's just a tension that intrigues me. I haven't. Perhaps there isn't a clear decision between the two because we're doing both.
One thing related to that is, could we bait something? Is it possible to get it to come to us? But then what do you bait it with? What does it eat? And will you contaminate what you're looking for? I don't know whether you could bait something in a... No, you couldn't do that, could you?
Well, impossible. You've still got to actually get down to where...
Yes, that's true.
You're
right. I've got a question next to that, because you're talking about how you search for hydrothermal vents, and you can see the smoke and the various signatures, even chemical signatures, quite high up. And that's actually coming from the hydrothermal vent. There's material from the vent getting to the surface. And in Enceladus, with this research, which if it was correct about the silica particles, then those silica particles have been on the surface between hot rock and the ocean. They get into the plumes between a few months and at most years. And then, so the question was, it's not back on the Earth, because if you were to search for life, the oceans are full of life anyway. But if you can imagine that you've got a place where the hydrothermal vents are the only source of life, if you've got silica particles getting into space, there's a chance the life could be getting there as well. How easy is that?
First thing, sort of in answer to that, on the technical side is, plumes will go up until they're neutrally buoyant, and then they spread horizontally.
Yeah.
But the situation on Enceladus seems to be that Well, there seems to be some form of heat associated with those ejector.
Maybe going all the way to the surface.
Yeah, I'm not quite sure, how. Well, obviously, no one's sure.
No,
about how that's going on.
Just about idea, yes.
I mean, the space environment, it's a shame Charles is not here because he'd probably be more able.
And you've also got the lower gravity, which we can't simulate on Earth. So
I mean, there was one article I read when I was researching the topic where it suggested that once that material is ejected into space, I mean, it starts to basically break down pretty fast. And one of the issues with sampling even those plumes on Enceladus is you have to fly by at sufficiently low altitude to pick up a decent quantity of the material. So I think even if there was something there, it's still a massive challenge to actually pick up, say, cellular material or something like that.
I mean, Cassini has gone below 50 kilometers, I think.
Yeah, but
You're talking about lower than that.
Yeah, you need to go lower than that, I think. I can't remember the exact figure I pulled out the other day, but I mean, it's close. And I think what Andy's getting at is, are you better actually, looking for chemical signatures of, basically the way that life pulls things away from, their natural chemical equilibria. So there's a better strategy to simply look for those disequilibrium situations. The issue with that, I can see, and Doug, you're probably a better person to comment about this. The issue about that is that, I mean, so far, our actual knowledge of how those oceans are made up, what the chemical constituents of them are, is pretty flimsy. I mean, we've got the Cassini data, but there's still a lot of conjecture about what's actually there. So
yeah, I mean, you are seeing again sort of still some knowledge. I mean, there's what the Sentinel satellite system, and part of that is testing some new sensors that look at contaminants. So that might actually help us a lot in the future. Get that sort of sharing and modelling technology, looking remotely. We're not going to be able to actually bring a bottle of water back and analyze it, or a bottle of gas back and analyze it. So you tightly remote system.
There are the sample plume collection plans, but then you've got a 12-year delay to get the sample back, and it could deteriorate in that time, especially with radiation and heat temperature.
So as far as I know, or as I can imagine, you will only sample the very light molecules, because the more complex molecules, they have a much lower velocity. So they do not fly to an altitude of 50 kilometers, only the light ones, because they are slower, because energy is equally distributed. And you will not sample those ones, and maybe you will get a wrong picture of the whole system if you only measure very light molecules and then say, okay, they are organic, but it's not very complex. So you would need really a deep sample, but that's risky. I think we must have a stepwise approach. So surely a lander and a melting probe is not the first step in exploration. I think the impactor probes, they are a good solution for a first step, because they are not so expensive. You can send an impactor maybe to Enceladus for $1 billion or something like that. It's still expensive, but come on, we are 40 million or 320 million Americans and 400 million Europeans, so that's €1 or $1 per person, and that's over 10 or 20 years, so it's really not so much money. And if you compare it with a lander, I think a lander would be in the order of, I doubt that it can be done for 5 billion. I think you are more in the correct order of 20 to 50 billion euros or dollars to send a lander on the surface. And so we first have to pluck the low-hanging apples, and then we can go for the higher ones.
Yeah.
And we have to escape also this what you mentioned, this space spiral that is going on. Missions become more and more complex, so they become more expensive, so they have to be more reliable, and they become more expensive, and they have to become more reliable, and this is always ongoing. Nobody accepts a reliability of 90%. Everybody wants to have 99 or 99 point something percent, but if you can do it with a reliability of 90% for half of the money, then your expected outcome would be much higher. And if you look at Mars, for example, we cannot land at the most promising locations on Mars because it's too dangerous. We need a flat area where we can safely land, and if you would have a cheaper spacecraft and with a lower reliability, you can send 5 of them, and 1 or 2 or 3 will work. And this is, I think, the better approach, but in the space agencies, they are going the wrong way to more reliability and more expensive missions.
I must say, as a marine biologist, some of the numbers that have been flung around today have been quite amazing. I mean, we can't find 1 billion to map our own oceans, let alone moons out around Jupiter and Saturn. So, I mean, it's a big challenge.
Yeah, but there are environmental satellites in the same order of magnitude. If you look to Envisat or the NASA Terra satellites, they are in the same, they also cost $1 billion.
Now I want to thank Profile there for, well, this gentleman over here who did all the main organisation, and I also want to thank Vox here who are going to produce the video to circulate with everyone, and the people that aren't here. So thank you both for you two work, and for Alex for
thank you.
suggesting this wonderful event. I'm most inspired.